So we'll discuss that more as it approaches. Okay, let me review this a little bit, and then Stephen will take a question that you might have. So let me review a little bit what we were talking about. So we discussed a very important idea, the distinction between coherent superpositions or quantum superpositions of different alternatives and statistical mixtures of different alternatives. That's the language we use, and it has an important operational meaning. Okay, so if we think about, for example, a spin 1/2 particle, that's all we've really discussed to date. And so if we have a pure state, we've said that could be described by this ket, which generally could be in a coherent superposition of the two bases, or orthogonal basis states. Okay? And we know from the Born rule how to calculate the probability of finding one of the outcomes in a projective measurement, right? And that's given then by the squares of these amplitudes. And if we look at, for example, the probability to find spin up along x, as we said from the very first lecture, there's an important contribution to this probability which doesn't follow from classical logic. Okay? So this probability has pieces in it that we would argue from the point of view of logic. There's some probability to find spin up along x, given that the spin was spin up along z, times the probability it really was spin up along z, plus the probability that we would find spin up along x, given that the spin was really spin down along z, times the probability that it is spin down along z. And then there are these terms. These terms which have no classical logical analog. They are the quantum interference terms between those two alternatives. Okay? And that's the hallmark of the fact that these interference terms are there is the hallmark of the quantum superposition. The fact that these two alternatives were not locally real, we just didn't know which one they were. They exist in some quantum limbo state that we don't really understand, and that has impact on this probability. For example, if those two probability amplitudes were, say, equal to 1 over root 2, then the probability of finding spin up along x would be 1. We would definitely get that outcome. And we can think about that as there is constructive interference between those two alternatives. In contrast, if the amplitudes were equal but there was a minus sign there, then the probability to find spin up along would be 0. There would be complete destructive interference between those two alternatives. Okay. Okay, so that's the superposition, the coherent superposition, and that's being contrasted with what we call a statistical mixture. And a statistical mixture, what we say is that, the preparer, we imagine this scenario, which is a possible thing that one can do, and one does do in some, say, quantum communication protocols, where the preparer has the ability to send you, the receiver, you're typically called Bob, I'm typically called Alice, because there are A and B, and those are the names we always use. So Alice prepares either this or that, and she doesn't tell you what she's doing, but she does so with a coin flip. that point that may or may not be a fair point. It has some probabilities. And what we showed last time is that we could describe the state of the system in that case not as a quantum superposition of these two alternatives, but as a statistical mixture which is represented mathematically by this thing we call the density operator, or we can call it the state operator. It is our representation of the state of the system. It's the thing that we use in order to calculate probabilities of measurement outcomes. And the way we do that, the generalization of the Born rule to the case of statistical mixtures, is that the probability is given by the diagonal matrix element, or the expectation value, if you like, of the density operator in the state of consideration. So if we wanted to find the probability of finding spin up along X, this is the rule. Okay? And doing that, we find this. And that's just the classical logic piece. It doesn't have the interference. So what distinguishes the statistical mixture from the quantum superposition is the lack of interference between those two alternatives. Okay? That's the key point. And any state of the system, whether it's a coherent superposition or statistical mixture, is a density operator. So the density operator is the most general way of writing a quantum state. It takes into account all possibilities, quantum or classical kind of statistics. All right? And so, for example, a pure state is a state which is just given by this outer product between Ken and the bra for some particular state in Hilbert space. And I just wrote this out as an example in the context of writing it in this basis, so I expanded psi in this basis, which I can always do. And when I do that and I write out all the terms, you see explicitly that this density operator has diagonal elements which look like the statistical mixture of spin up and spin down. It looks just like this. But then it has off-diagonal pieces, and those off-diagonal pieces are the things that we call the coherences. They express the potential for observing interference between those alternatives. Okay? All right, question.
Can those coherent coefficients be negative?
Sure. I mean, in this particular case, they could be, they're generally complex numbers. They generally have real and imaginary parts, and they generally, they're positive or negative. I mean, for example, what we showed, oh, excuse me, pardon me, this is boo-boo, owie, mistake. That should have been that. In this case, these coherences would be negative, right? This would be -1/2 and -1/2. And that was the case where we had destructive interference. It could be pure imaginary. It could be anything, any complex numbers. Yeah.
But the trace of the density operator for a pure state must equal 1, right?
Right. We'll get to that in a moment.
So long as those two the top two
well, so these are real numbers.
So long
because they are the absolute squares of complex numbers.
So long as they're equal 1, the state's fine.
It's normalized, indeed. We'll get to that in a moment. All right. So what we have here is that we said that we have just so statistical mixtures. We could have whatever we like. We could say we can have an ensemble of possible pure states, psi I. We could have as many as we like. prepared with probability pi. So we have this picture of the preparer sending us a pure state, but not telling us what she's sending us. She just tells us the probability she's going to do it. And the state we would assign, if that was the case, would be this. If she sends all, if she tells us there's definitely going to send one state with probability 1 and all the others with probability 0, that's a pure state. Otherwise, it's a mixed state. So this is generally what we would call a mixed state. If not all the probabilities are, or only, if the probabilities aren't 1 and 0 for all the rest, then it's mixed. Otherwise, it's called pure. And moreover, we have that so in a basis, so let's just talk, we're talking generally now, not just about 2.5. Let's just say we have a d-dimensional Hilbert space. Then, and let's just say we have a basis E alpha. Alpha goes from 1 to D. Then we could look at the matrix elements of this operator. So just to emphasize the facts, the diagonal elements this is the probability to find E alpha in a projected measurement. That's the Moore rule. And the off-diagonal elements are what we call the coherences. They are they in some sense represent the potential to see interference between alternatives E alpha and beta. Okay. Tells you how much interference you might see in some case. And again, if I look at this from the point of view of the statistical mixture over here, then this is equal to sum over all the members of the ensemble in this guy. That's that, right? So I'm just weighting, would be the Moore rule for a particular pure state, but I don't know which pure state she sent me. So I have to average over them. Clear? And that I could write, if you like, as this. C alpha squared. Or I've written psi, or this is particularly type 1. I is equal to the sum over alpha, C alpha, to the ith guy, E alpha. Okay. Moreover, the off-diagonal element here sum over this di psi I data. That is equal to the sum over, so let me just write this as the ensemble average of that for all those guys. That means averaged over the ensemble. Now I have this, C alpha I, and this is C beta star. Which is, if I write this, each of these complex numbers as having a magnitude and a phase, is right? I just wrote each of those complex numbers as having a magnitude and a phase. And so, again, to emphasize, the key point of the coherences is that they have something to do with the phase relation. Coherence and phase are intimately related. I mean, you know that from, or maybe you know that from the notion from wave interference in classical wave theory, say in optics. If we talk about a coherent field, it's a field that has a well-defined phase. And the fact that the phase is well stabilized means that you can see interference between different wave paths. But if the phase is jiggling around in some way and not well defined, then you don't see interference between the waves, right? And that's what this is saying over here. This coherence is the ensemble average of this guy over all the members of the ensemble. And if the phase relationship is not well defined between all members of the ensemble, then it will tend to average out to 0. Okay? So there's this intimate relationship between a well-defined phase between the probability amplitudes and whether or not you can see interference between those alternatives. All right, so let's say a few more things now about the density operator, what its properties, what are its properties from a mathematical perspective. Firstly, what can we say? Well, if we look at this operator over here, the density operator written this way, I'll just write it again over here. Well, firstly, it's clear that this is Hermitian. Right? Why is that clear? A Hermitian operator is one which is self-adjoint in finite dimensional space. Why is that obvious?
Because P is real.
Because P is real. Okay, these are real numbers. And we have an ensemble of possible states which sum to 1. That's another thing. And when you take the adjoint of this goes back with this goes back to itself, right? So it's Hermitian operator. The other thing I can say is that it's a positive operator. Positive operator is one where the expected value of rho is non-negative for all possible vectors. Is this the case? Sure, because, well, this is equal to the sum over I, pi, and and this is a positive number, this is a positive number, or it's something, it's definitely not negative, it could be 0. So, I mean, it's a weird thing. We call them positive operators, but we should really call them non-negative operators, because it could be 0. That's just the jargon that we use. All right? And as that means, of course, that means that two things. If it's a Hermitian operator, then it's a normal operator. And so that means that rho can be diagonalized. And its eigenvalues are non-negative. Those are two things that immediately follow. Right? So if what that means is that in dimension D, rho has D eigenvalues, and its eigenvectors can always be chosen orthonormal. Right? That's what we discussed in the first week or so of class, that Hermitian operators have can be diagonalized. It has D, I should say, in this case, real non-negative eigenvalues, and that we can always choose them to be orthonormal. Okay, if they're for different eigenvalues, they're automatically orthogonal, but we can always, if they're not, we can always find their orthogonal basis within the degenerate space. Okay, so let's call the eigenvalues of rho let's say the eigenvectors are, and we call them u lambda, and the eigenvalues lambda. And we can always express rho in the basis of its eigenvalues, right? Or basis of its eigenvectors, I should say, right? So, what can you tell me about this representation? How can I interpret this? Well, it looks just like that. Okay? So, rho is always, can be thought of as a statistical mixture of its eigenvectors with mixing probability given by its eigenvalues. Now here's an important point. These guys need not be the same as these guys. Okay? Now this is confusing, and let me explain why. I can tell you what I'm mixing. Here I am, I'm Alice. I'm going to send you a little spin up along Y, I'm going to send you a little spin up along Z, I'm going to send you a little spin down along 45 degrees, I'm going to send you a little bit of 40 spin up along this axis. I can send you whatever I like. And the vectors I send you don't have to be orthogonal vectors. They can be, and I can send you a million of them. Okay? For spin 1/2. I can send you a million different possible spins, and I can tell you beforehand that's what I'm going to do. So this ensemble of decomposition doesn't have to be an eigendecomposition. It could be whatever it likes. One thing you learn from this is that there is not one unique ensemble for a given state. In other words, there are many, many, many different ensembles. In fact, an uncountably infinite number of different possible ensembles which all lead to the same density operator. You could not tell the difference. That's one of the things you're going to see in your homework. And that's because the classical probability and the quantum probability are kind of getting mixed up together. So the ensemble decomposition is not unique. Now we can ask, what are the conditions on the ensemble such that they give the same density matrix? And we can quantify that. We can say these two ensembles would give the same state. Okay? It is a very puzzling thing. Now, of course, the eigendecomposition is unique up to degeneracies. So if all the eigenvalues are non-degenerate, there is a unique way of thinking about this as a statistical mixture of the eigenvectors. Yeah?
Is this related to Adrian's question where he asked, you could, if you backlines the density,
Yeah.
you could continuously rotate it into that, or I mean, you could change any into, a diagonal matrix, but
Yeah.
it's not.
That's not necessarily that matrix. And the reason is if they're not orthogonal. Okay, so the example I gave here, go back over here. Let's bring the camera over here. This density matrix is in its diagonal representation. Okay. But let me come back over here then and say, suppose this is the problem I think you're going to get in your homework. Let's say I have rho is a half spin up along z and a half spin up along y. Okay? That's a perfectly good density matrix, a perfectly good density operator. That is not, these are not the eigenvectors of this operator, right? If I look, for example, what happens if I act this on this? Well, I get, in this case, a half spin up along z plus a half spin up along y times that, which is 1 over root 2. Right? And so I don't get back the same vector. That's not an eigenvector. In fact, you could see it also in a matrix representation. Suppose I wanted to express this operator as a matrix, as a 2 by 2 matrix in the basis of choice. Here's a basis. Let's say spin up and spin down along z. So what does this operator look like in that basis? If I write it as a matrix.
1, 0, 0, 0.
Everyone see that? This is in the basis. So in the basis, up and down along z, that's the projector. What does this projector look like in that basis? Well, that's a little trickier. So the way to do it is, there's lots of ways to do it. One way to do it is to write this as rows and column vectors. Okay? So this vector, if you remember, is 1 over root 2 and I over root 2. That's the column vector. Oh, actually, sorry. That's the row. This is the K. So it's a superposition of spin up along. Let me do this more slowly. Because what the heck, let's review this. Aside. Let's let M be this operator. And I want to write a matrix representation of this in the basis. There's lots of ways to do this. How do we do it? Well, we could insert a complete set, right, on the side, or we could just write out the matrix elements. We could say this is this, row, column, row, column, row, column, right? This is one way to do it in a somewhat systematic way if you can remember things. Yeah.
Could you just substitute in what y in terms of z basis?
That's what we're doing. Yeah, as I say, there's lots of ways to do it. I'm just writing it out systematically, right? If you remember how to write an operator in basis. There's lots of ways. I'll show you the other way, just so because we have different approaches at our fingertips and we interchange them depending on which is the most convenient thing. Okay. So what we remember is that we have to look this up or remember it, which I do remember because there's just a few of them I do remember, and this is what I remember. Okay. So with that said, so this is equal to, this operator over here. This is equal to this. This is equal to this. This is equal to this, and this is equal to that, right? So this is equal to what? This is equal to a half on the diagonals. Okay, this is the square root of those amplitudes. And then I have this times the conjugate, and this. Okay. So, and as I was saying just a moment ago, I could write this, and this is what was being suggested, and this was how I was originally going to do it, because if it's just an outer product of two vectors, I don't have to go through all those tedious steps. I could just say this guy is equal to this cat is equal to 1 over root 2, I over root 2, and then I have the bra. And then I take the outer product, and I get that. It's another way of doing it. You have to learn how to use these different techniques and decide which one's the most rapid and convenient. Okay? So, what was the point of this exercise? The point of this exercise is this is not a diagonal matrix. So, we write this out. This is this plus this. It's not a diagonal matrix. Even though it's a statistical mixture of these two things, it's not diagonal. Well, what does that mean? It means that there are coherences. But coherences between what? They're coherences between spin up and spin down in the Z basis. And that's because this state, although it doesn't show interference between these alternatives, it shows interference between these alternatives. And that's what's being captured in the off-diagonal elements of the density matrix. Yeah, Zeke, you had a question?
So I mean, when I first saw this, I thought that for mixed state, the off-diagonals would be 0, but
Yeah.
that's not true.
Exactly.
Okay.
Yeah, that's true. It does. So there's a degree of mixedness. We're going to talk about that for a completely mixed state. So there is a continuum of possibilities. Perfectly pure, they have off-diagonal element, right, and then in some basis. And then we have maximally mixed. And those states have no off-diagonal elements in any basis. And then you have partially mixed, or partially pure. But, as we said, we can always think about it as a statistical mixture of its eigenvectors. And that's just, in some ways, a unique up to degeneracies. Now, let's see, what else do I want to say? Yeah, notes here. I know.
So if looking at a pure state, partially mixed state, matrix, I mean, how can you tell which by just looking at the matrix?
Good question. We'll get there very soon. It's an excellent question. It's an excellent question. I would say one thing, you can't necessarily tell by looking at the matrix, because that's a basis-dependent property. And we want something that's independent of basis. It's the property of the operator, not the representation in a basis. It's important to understand that distinction between basis-dependent properties and basis-independent properties. We'll get there in a moment. All right. Okay, yeah. Oh yeah, that was the point I forgot to mention. That was the point you raised earlier about normalization. So, density operators are Hermitian operators. They're positive Hermitian operators. We can also normalize them, and the same way that we said that when we talked about kets, we said we typically normalize them so that we can easily calculate probabilities. Okay, so with normalization chosen so that this equals the probability. I won't trip. Okay? And so that, what we mean then, is that if we have a basis, or I guess I was calling it alpha. So what we want, if we have a basis, the alpha, then it should be that the sum of all of these, which is the probability of finding one of the alternatives, should be 1. Right? That's what we mean if we want that to be a probability. So that's how the states are normalized. And as we saw, this is just the sum of the diagonal matrix elements, which has a name. It's called the trace. So this is the trace of rho. So we choose our density operators to be normalized by setting their trace to be 1. Now, a point, of course, is that we can always normalize afterwards. Okay, so if some reason we had some operation where we got a density matrix that wasn't normalized, we could always renormalize it. In the same way that when we did projective measurements, or measurements in general on kets, we had to renormalize, right, in our Bayes rule and stuff like that. So we just find out what the trace is and divide by it so that the trace is A1 after the fact. All right. All right, so now I want to say something about pure versus mixed states. So for a pure state, we said there is some ket such that rho is then just the projector on that ket, right? What can you tell me about the eigenvalues and eigenvectors of this state? So remember, this is a ket, and it's a normalized ket, if this is a normalized thing, right? So the norm of this is 1. Not that that matters much, but I just wanted to remind you of that. Is this a normalized state? Does the trace of this equal 1? How do you tell? Well, remember we proved in one of the problem sets that the trace of an outer product is equal to the inner product. That's a very, very useful tool. And I always think about it as outer products with inner products. And I always put a little in there to remind myself that I'm clicking them together when I do the trace. I make this simple. So, what is the trace of this? It's just that. Okay.
And the trace of a mixed state is always left in the correct or
No, it's equal to 1 as well. Because the trace of a, so let's say we have a mixed state. And let's say I wrote it as, I can write it in any ensemble decomposition I like. I'll write it in, there's some ensemble decomposition, I don't care whether it's the eigen decomposition or any other decomposition I want. What is the trace of this mixed state? What's the trace of that? It's the sum of the traces. Trace is linear, so I can bring it inside the sum. It's one of the things we proved. And the trace of this is 1. And so this is the sum of all the probabilities in that with 1. So for a mixed state, the trace of 1 is as well. The state is normalized, mixed or pure. But now, the question or a question I wanted to get to is, what are the eigenvalues and eigenvectors of pure state? So here's my state, it's pure. Can you see one eigenvector?
I want to say 1, like, yeah. It would be
Eigenvalue is 1. What about the eigenvector?
just psi.
Psi. So psi is an eigenvector of rho pure. That's obvious. Because if I operate this on this, I get it back. Right? And the eigenvalue is 1. Okay, so that's one of the eigenvectors. And that's one of the eigenvalues. What are the other eigenvectors? If it's a d-dimensional space, what are the other eigenvectors and eigenvalues? Well, let's just say we had a basis, and this was one element of the basis. Okay? And then we have all the other d-1 basis elements, all of which are orthogonal to this. What happens when I hit row pure on those?
Zero.
You get 0. So all the other eigenvalues are 0. So for a pure state, and we can see that over here. Come back to this one. This is the general form of the density matrix, or the density operator, written in its decomposition in terms of its eigenvectors and eigenvalues. And if it only has one term, if it's a pure state, then one of these eigenvalues is 1, and all the others are 0. Then it just has that one term in it. So for a pure state, and that's important, this only has one eigenvalue that's 1 and the rest are 0. So for a pure state, let's put that on the front board. This is important. Not the stuff on the sides is not important, but somehow I have this feeling. So one eigenvalue is 1, and the corresponding eigenvalues or eigenvector is psi. And all the rest all other eigenvalues are 0. And it doesn't matter, but we choose any eigenvectors we like that are in the orthogonal complement to this. Anything that's orthogonal to that is an eigenvector, it doesn't matter. We usually wouldn't even write it down because it gets weighted by 0, so who cares? So, question. What is the matrix representation of this pure state in the basis of its eigenvectors? What does it look like?
A 1 on one of the diagonal places wherever psi is in the basis. And 0
So
the
we
rest.
would just write that one as the first basis element, and then all the others, some psi perp, doesn't matter. And it's that. So it's got 1s, and it's 0 everywhere else. Now this comes to a point, Zeke, that you were raising. This is a pure state. It's at the most coherence that you can have, but its off-diagonal matrix elements are 0. This is a point I'd like to reemphasize. It's not right to talk about the off-diagonal matrix elements. It's off-diagonal matrix elements with respect to a basis. If it's a pure state, that means in some basis, it will have very big off-diagonal matrix elements. Doesn't mean that in every basis it will have big off-diagonal matrix elements. And in fact, in the basis of its eigenvectors, they're 0, because there's no interference between those different alternatives, because there's only this alternative. So, so now I want to come to the a question that Stephen raised. He's not here at the moment, but maybe he'll come back. Let's see. And that is, how do we distinguish, because we can't just look at the matrix and look at it unless we're somehow geniuses about matrices generally, and know whether this was a pure state of I mean, look at this one, I can see it's a pure state because it's got 1 on 1 diagonal element and 0, that's pure. But generally, if I looked at that matrix, I wouldn't know offhand how pure or mixed that was if I added those things together. So what is it? What is a defining feature of the density operator that is a function of the state itself and not the basis with which we use to represent the state? So let's consider consider the square of the density operator. Okay, let's just consider that. Well, I can always do a function of an operator by expressing it in terms of its diagonal representation. If it's a Hermitian operator, I can always do that, and then just do the square on the eigenvalues. Right? That's what we learned. So this is the sum over all the eigenvalues of the density matrix. Okay. So, what is the trace of rho squared? Well, that's 1. So this is equal to the sum over all the eigenvalues times squared. So what can you tell me about that? If it's a pure state, what is the trace of rho squared? 1. So if it's a pure state, the trace of rho squared well, what if it's mixed? Well, if it's a mixed state, what can you tell me about the eigenvalues? I guess I should have said that over here. What are the eigenvalues? What can you tell me about them? Well, they're positive numbers, right? Because we said it's a positive operator. And it's normalized. And if it's normalized, the trace means it's the sum of the eigenvalues. The trace of rho is equal to the sum of the eigenvalues. Right? And that sum has to equal 1. So what can you tell me about each of the eigenvalues? They have to be less than 1. Right? They could be 0. For a mixed state, all of these are less than 1. Yeah.
But they're not necessarily the probabilities.
They're not necessarily, they are the probabilities of a mixing in the eigenbase, but they're not necessarily the probabilities in what the original mixing that you did. That's true. Okay, but the eigenvalues, which are properties of the operator, are all less than 1 if it's a mixed state. So what does that mean about the trace? What about the trace of rho squared? What can you tell me about this sum? It's got to be less than 1. So the telltale sign of whether or not the density operator corresponds to a pure state or a mixed state is by looking at the trace of rho squared. I mean, you can look at the eigenvalues, but the quick way to do it is look at the trace of rho squared. And this has a name. This is called the purity of the density operator. You could call it also the mixedness, but it's typically called the purity. And so if it's a pure state, then the trace of both the purity is 1. And if it's a mixed state, the purity is less than 1. If it's a statistical mixture of some kind.
So what if it was maximally mixed? Would it-
Good question. What does it mean to be maximally mixed? Excellent question. That's the next thing.
Zero?
Well, that's a good question. Let's find that out. That's exactly where I was headed. So, what do we mean by a maximally mixed state? If it's maximally mixed, that is, what we mean by that is an equal statistical mixture of D orthogonal states. That's as mixed as you could be. For example, 50% spin up along Z, 50% spin down along Z. That's completely mixed.
So all the lambdas would be equal?
Indeed. So what are all the lambdas? In this case, it's a good, excellent point. So what are the lambdas in this case? They're all equal. And what do they have to be? They have to sum to 1.
1 over D?
1 over D. Right? Excellent. So the lambdas are 1 over D for all lambda. So how could I write then a representation of the density matrix for maximally mixed? Well, it's a sum over all the eigenvalues, each eigenvalue times the eigenvector. And the eigenvectors could be anything I like that are form of basis. Okay? Now, since it's independent of lambda, I can bring this outside the sum. And so that's 1 over D, the sum over lambda, this. But this is familiar object. What is that? That's the identity. So a maximally mixed state is just proportional to the density operator. I mean, to the identity operator. It is 1 over D times that. And moreover, this state, it looks the same in all bases. This is always what the matrix looks like, which means this off-diagonal matrix elements are 0, absolutely 0, in all bases. So the matrix isn't 0, but its off-diagonal matrix elements are 0 in all bases, if it's maximally mixed. So it doesn't matter whether I thought about it as, so here is the point, or a point. I'm Alice. I'm going to send you either spin up along X or spin down along X. I'm going to do that with a fair point. I'm Alice number 2. I'm going to send you spin up along Z with probability 1/2, or spin down with Z with probability 1/2. You couldn't tell the difference. You would get random results. No matter what you did, your result would appear random to you. It would be completely a random 50-50 no matter what measurement you did. Whereas from Alice's point of view, she kind of knows. If you do a Z measurement and she sends you Z, she knows what you're going to get, but you don't. Okay? So those are examples of 2 ensembles which your statistics look exactly the same. All right, so now what is the trace of rho squared? So for a pure state, this is 1. For a mixed state, it's less than 1. But what's the smallest possible value of purity you can have when I have a maximum mix?
0?
No, that's a good guess, but not true.
What about 50?
1 over D.
So let's just look at this. We have to do the sum over all the eigenvalues.
What if you have an infinite dimensional matrix?
I'm saying for dimension D.
So it's not.
It's not, it's dimension D.
Well, it would be the sum of 1 over D squared,
Yep,
and then you add them D times.
Yep.
So that'll just be D over D squared.
yep. Which is D, 1 over D. Excellent. So the minimum value of this, the purity at smallest is 1 over D. Rho is max next. So you can't get 0. The purity is always something, but it doesn't mean it's just a small, but that's just the number we get. But the off-diagonal elements are absolutely 0 for maximum mixed state, and that's what's important. Okay? But the purity is a measure of how mixed the state is. Now, I should just, there's something I meant to say earlier, but I hadn't, but let me just say it now. Some of these concepts are not, this is not purely a quantum mechanical idea. This is something that you might be familiar with if you've studied optics. And that's the notion of partial polarization and polarization. Suppose I have the light that's coming out of this light bulb, and I looked at it through polarizing and analyzing. If I looked at it at, say, vertical, half of the intensity would come through. If I looked at it horizontal, half of it would come through. Would come through. And but it's not a coherent superposition of vertical and horizontal. It's a statistical mixture of those, right? It's not polarization at 45 degrees, because if I put it at 45 degrees, still half would come through. So it's a completely mixed polarization. Now I can partially polarize it. The light that reflects, I mean, you may have, if you've studied optics, you know that when you reflect, some part of it reflects differently than the other, and it would be partially polarized. So these concepts are classical wave concepts as well. Where they become quantum is when we think about them as events and probabilities, rather than fractions of wave intensities. All right. Excellent. Oh yeah, next. So another thing we want to talk about here is, so we can calculate probabilities if we have the density operator, but what about expectation values? So what we said here was that given, or so, this is the probability to find eigenvalue A associated with eigenvector A of some observable. This is the Born rule. So, this is the probability. I'm going to find it a little scripty. I could rewrite this in a way that is useful. This is equal to the trace of rho with that projector, right? Because so another way of writing this probability is the trace of rho with the projector on that space. So this is the projection operator. Now, if I have a remission observable, then we can decompose it in terms of its spectral decomposition in terms of its eigenvalues. Now, I can even allow those things to be degenerate. That projector could be onto a degenerate subspace associated with that eigenvalue, if I like. It doesn't have to be. It could be a 1D projector like this, or it could be whatever. So, the expected value of A the expectation value, well, that's equal to the sum over all the eigenvalues times, that's the average value, the probability I'm going to measure that in that state, right? By definition, that's what we mean by the expectation value. It's the average value. And this is equal to this. Right? That's what we just said. And the trace is linear. So I can bring it outside the sum. Rho doesn't depend on A, so I can report outside the sum. And this is equal to this. Right? I brought rho trace outside the sum, and then I put rho outside the sum. And this is the observable A. So, the general way of expressing the expectation value when I don't have a pure state, but I have a general state, which might be mixed, is to look at the trace of the observable with the state. Okay? And the Born rule can be expressed as, if I have a projective measurement, the probability I'm going to see that outcome is the trace of rho with the projector. Can anyone guess if I have a general POVM with POVM elements E mu? What is the probability of seeing outcome mu? What do you think, Mark? Trace of rho E mu. Exactly. Terrific. I mean, when we had it as a psi, we wrote it like this, right? Now this is the generalization. So now you know the most general form of Born's rule, that this is the Born rule. This is really, really it. It takes into account the fact that your state might not be pure, and it takes into account that your measurement might be projected. That's the most general form. And that's the most modern way of saying psi star psi, which you learned in third grade. All right. In the last 2 plus whatever minutes, I wanted to say one thing about now time evolution. So what we said was, if we have a closed quantum system, pure states are mapped by a unitary operator. I'm going to change my notation a little bit. I'll fix it in the notes as well, because that's a notation I prefer to use. Let's say we have the state at time t0. And we want to know what is the state at some later time t. They're related by a unitary operator, which I'll just split these two. Okay? So t greater than t0. So this is a unitary operator. How does this look just from the point of view of the density operator? So the state at time t0 was this. The state at time t is a pure state. And that state is given by u and u delta acting on the bra. Right? And this in between is this. So we have, for this evolution on a pure state, that the state at a later time is this unitary map on this. Okay? The unitary transformation on that. For a general mixed state, which could be in any ensemble composition I like, then what is the state at a later time, if it's a closed quantum system? Well, each one of these guys evolves like this. And then that could be brought outside the sum. So it's the same thing. So if I have a closed quantum system, then this is the evolution of the state, no matter what it started as. Okay? This is what we call unitary evolution. Now, what about if I have a closed quantum system, what happens to the purity? How does the purity change as a function of time? That's the last thing I want to talk about. It doesn't, and how do we prove that? The trace of we want to find what is the trace of the state at a later time. That's what we'd like to know. So let's plug it in. That's equal to the trace of u rho at t0 u dagger times the same thing again. Right? And now u dagger u is 1, right? So this trace of rho at time t, rho squared at time t, is the trace of u rho squared at t0 u dagger. However, we know, because we did the homework, that you could do the cyclic permutation, right? So that's the trace of u dagger u rho 0 squared. And that's the identity. Yay, yay! You can prove. So when you have unitary evolution, the purity is unchanged. And that's what we expect. That's sort of how we defined the fact that the evolution of a closed quantum system was unitary, because we wanted to say it kept pure states to pure states. But moreover, it doesn't just say pure states to pure states. Whatever mixedness you have, that mixedness is unchanged. And that's because we're neither losing information nor gaining information. Okay, what we'll talk about briefly to conclude this discussion next time is that, of course, not all evolutions preserve purity, because for God's sake, how do we get a thermal state when we take the silver atoms coming out of the oven? So we want to talk briefly about that and the idea of equivalence. So we'll get to that. So we'll discuss that more as it approaches. Okay, let me review this a little bit, and then Stephen will take a question that you might have. So let me review a little bit what we were talking about. So we discussed a very important idea, the distinction between coherent superpositions or quantum superpositions of different alternatives and statistical mixtures of different alternatives. That's the language we use, and it has an important operational meaning. Okay? So if we think about, for example, a spin 1/2 particle, that's all we've really discussed to date. And so if we have a pure state, we've said that could be described by this ket, which generally could be in a coherent superposition of the two bases, orthogonal basis states. Okay? And we know from the Born rule how to calculate the probability of finding one of the outcomes in a projective measurement, right? And that's given then by the squares of these amplitudes. And if we look at, for example, the probability to find spin up along x, as we said from the very first lecture, there's an important contribution to this probability which doesn't follow from classical logic. Okay? So this probability has pieces in it that we would argue from the point of view of logic. There's some probability to find spin up along x, given that the spin was spin up along z, times the probability it really was spin up along z, plus the probability that we would find spin up along x, given that the spin was really spin down along z, times the probability that it is spin down along Z. And then there are these terms. These terms which have no classical logical analog. They are the quantum interference terms between those two alternatives. Okay? And that's the hallmark of the fact that these interference terms are there is the hallmark of the quantum superposition. The fact that these two alternatives were not locally real, we just didn't know which one they were. They exist in some quantum limbo state that we don't really understand, and that has impact on this probability. For example, if those two probability amplitudes were, say, equal to 1 over root 2, then the probability of finding spin up along x would be 1. We would definitely get that outcome. And we can think about that as there is constructive interference between those two alternatives. In contrast, if the amplitudes were equal but there was a minus sign there, then the probability to find spin up along would be 0. There would be complete destructive interference between those two alternatives. Okay. Okay, so that's the superposition, the coherent superposition, and that's being contrasted with what we call a statistical mixture. And a statistical mixture, what we say is that, the preparer, we imagine this scenario, which is a possible thing that one can do, and one does do in some, say, quantum communication protocols, where the preparer has the ability to send you, the receiver, you're typically called Bob, I'm typically called Alice, because there are A and B, and those are the names you always use. So Alice prepares either this or that, and she doesn't tell you what she's doing, but she does so with a coin flip. That coin that may or may not be a fair coin. It has some probabilities. And what we showed last time is that we could describe the state of the system in that case not as a quantum superposition of these two alternatives, but as a statistical mixture which is represented mathematically by this thing we call the density operator, or we can call it the state operator. It is our representation of the state of the system. It's the thing that we use in order to calculate probabilities of measurement outcomes. And the way we do that, the generalization of the Born rule to the case of statistical mixtures is that the probability is given by the diagonal matrix element, or the expectation. And that was the case where we had destructive interference. It could be pure imaginary. It could be anything, any complex numbers. Yeah.
But the traits of the density operator are pure state less equal 1, right?
Right. We'll get to that in a moment.
So long as those two the top two see.
Well, so these are real numbers.
So long
because they are the absolute squares of complex numbers.
So long as they're equal 1, the state's fine.
It's normalized, indeed. We'll get to that in a moment. All right. So what we have here is that we said that we have just statistical mixtures. We could have whatever we like. We could say we can have an ensemble of possible pure states, psi I. We could have as many as we like, prepared with probability pi. So we have this picture of the preparer sending us a pure state, but not telling us what she's sending us, she just tells us the probability she's going to do it. And the state we would assign, if that were the case, would be this. If she sends all, if she tells us there's definitely going to send one state with probability 1 and all the others with probability 0, that's a pure state. Otherwise, it's a mixed state. So this is generally what we would call a mixed state. If not all the probabilities are, or only, if the probabilities aren't 1 and 0 for all the rest, then it's mixed. Otherwise, it's called pure. And moreover, we have that so in a basis, so let's just talk, we're talking generally now, not just about 2.5. Let's just say we have a d-dimensional Hilbert space. Then, and let's just say we have a basis E alpha. Alpha goes from 1 to D. Then we could look at the matrix elements of this operator. So just to emphasize the facts, the diagonal elements patient value, if you like, of the density operator in the state of consideration. So if we wanted to find the probability of finding spin up along X, this is the rule. Okay? And doing that, we find this. And that's just the classical logic piece. It doesn't have the interference. So what distinguishes the statistical mixture from the quantum superposition is the lack of interference between those two alternatives. Okay? That's the key point. And any state of the system, whether it's a coherent superposition or statistical mixture, is a density operator. So the density operator is the most general way of writing a quantum state. It takes into account all possibilities, quantum or classical kind of statistics. All right? And so, for example, a pure state is a state which is just given by this outer product between Ken and the bra for some particular state in Hilbert space. And I just wrote this out as an example in the context of writing it in this basis, so I expanded psi in this basis, which I can always do. And when I do that and I write out all the terms, you see explicitly that this density operator has diagonal elements which look like the statistical mixture of spin up and spin down. It looks just like this. But then it has off-diagonal pieces. And those off-diagonal pieces are the things that we call the coherences. They express the potential for observing interference between those alternatives. Okay? All right, question?
Can those coherent coefficients be negative?
Sure. I mean, in this particular case, they could be, they're generally complex numbers. They generally have real and imaginary parts. And they generally, they're positive or negative. I mean, for example, what we showed, oh, excuse me, pardon me. This is boo-boo, owie, mistake. That should have been that. In this case, these coherences would be negative, right? This would be -1/2 and -1/2. This is the probability to find E alpha in a projected measurement. That's the Moore rule. And the off-diagonal elements are what we call the coherences. They are they in some sense represent the potential to see interference between alternatives E alpha and E beta. Okay. Tells you how much interference you might see in some case. And again, if I look at this from the point of view of the statistical mixture over here, then this is equal to sum over all the members of the ensemble in this guy. That's that, right? So I'm just weighting. This would be the Morton rule for a particular pure state, but I don't know which pure state she sent me. So I have to average over them. Clear? And that I could write, if you like, as this. C alpha squared. Or I've written psi, or this is particularly type 1. I is equal to the sum over alpha, C alpha, to the I guide, E alpha. Okay. Moreover, the off-diagonal element here sum over this di psi I data